Hello, everyone, and welcome to my presentation. I'm very excited to be getting this opportunity to present at the TURBOMOLE seminar series, my work that I've been doing in TURBOMOLE. And so basically, I'm a PhD student, Manas Sharma, in the group of Professor Marek Sierka at the University of Vienna. And I'm developing something called density functional embedding scheme for molecules and periodic systems. So the goal of my PhD is to investigate nonlinear optical properties of hybrid systems, such as a molecule adsorbed on a surface. So basically, we want a quantum mechanical description of these hybrid systems. And for that, I'm developing and implementing density functional embedding theory within TURBOMOLE. Also, this DFET, density functional embedding theory, will be coupled with wave function theory methods like Molar Placid, couple cluster single doubles, and real-time time-dependent density functional theory, or rt-tddft. And at this point, I would also like to point out that my work is quite closely related to a talk that we saw earlier by Professor Fabio Della Sala, where he had implemented FDE within the TURBOMOLE, and that has been also quite useful for me, but I'll mention how it's related or not related later on. So what is DFET in a nutshell? So it basically allows you to treat some portion of your system using a high level of theory, that is using a more accurate and computationally expensive method, while the remaining not so important surface or the environment can be treated using a lower level of theory that is computationally fast. And therefore, DFET finds its applications in hybrid systems such as solvated molecules or a molecule adsorbed on a surface. Usually in such systems, the focus of our study or the region of interest is small and just maybe the cluster or maybe a few atoms around it, while the periodic environment can usually be reasonably well described using lower levels of theory like LDA or GGA-DFT. The cluster or the molecule, however, requires going to some high-level methods like CCST or maybe hybrid functional DFT. If you decide to treat the entire system using LDA or GGA-DFT, then you get usually large errors in local properties such as the absorption energies of the cluster or maybe the excitation energies of the cluster. However, it is not only not necessary, but also computationally prohibitive to treat the entire system using something like CCSDT. In fact, I think there's only one code, that is PySCF, that allows one to do periodic CCSD. Otherwise, you cannot even do it, I think, with other codes. And that is also extremely computationally expensive. Also, there's this issue of periodic boundary condition where due to the PBC, you have this unrealistically high surface coverages. So this is also an issue. The solution to all these problems is provided quite naturally within the framework of density functional theory, where the properties of the system are determined using the electron density. So basically, we can partition the density of this total system into a cluster and an environment density, where the influence of the environment can be taken into consideration using an embedding potential, which is a function of both the cluster and environment density. I have implemented various strategies to construct this embedding potential, and to understand them, let us consider this model system. So here the benzene molecule would be our environment, while the water molecule would be our cluster or the region of interest. So in the method one, we relax the density of the environment, the isolated environment, then we plug this density into the formula of the embedding potential, and then we relax the cluster density in the presence of this embedding potential. And this method is actually approximate in nature due to the presence of approximate non-additive kinetic energy density functionals. Next, we have the method 2, where what I do is I relax the density of the total system using some lower level method like LDA-DFT. Then I relax the density of the isolated cluster, again using the same lower level method. And then I subtract these two to get the environment density. And then again, we plug the environment density just like before into the embedding potential. And then we relax the cluster density in the presence of this embedding potential, in which the environment density is a difference of the total and isolated cluster density. This method again is approximate in nature because Just the way of calculating the environment density has changed, but the presence of non-additive kinetic energy density functionals is still there. And now I would like to point out that this is actually just commonly known as frozen density embedding. And it has been around for quite like 30 years, I guess, since 1993 or 4. And this is what has already been implemented in TurboMole by Professor Fabio Della Sella. And yeah, but the difference is that actually, one difference at least is that it has been implemented for molecule-in-molecule embedding. So it utilizes DSCF and these codes in the TurboMole. However, my goal is basically to go towards the periodic. So we want to do something like molecule in periodic embedding. And therefore, we constructed this method 2 out of method 1, because this is more suitable for doing a molecule in periodic embedding, because we can calculate the total periodic density, and then we can subtract the isolated cluster density. So that is why the method 2 has been introduced. And then we have this method 3, where basically it is the same as the method 1, but the need of the approximate kinetic energy density functionals is now circumvented by using a projection operator that basically orthogonalizes the orbitals of the cluster with respect to the environment and vice versa. So the formula is something like mu times the overlap matrix of one subsystem with respect to the other subsystem, then the density of the environment subsystem, then the overlap matrix of the environment subsystem with respect to the active or the cluster subsystem. And one more thing that I should note here is that for this method to work, one requires a supermolecular basis, but then it gives exact results. So on one hand, you have a disadvantage, but on one hand, you see that at least it gives exact results. And also, it is quite common to perform a freeze and thaw procedure where the roles of the environment and the cluster are interchanged iteratively to get a more self-consistent embedding potential. Let's say we want to, or just see environment, the subsystem densities as well. So let's say you want to use the embedding potential in some higher level calculation, then you can perform this freeze and thaw procedure. For method 3, you will get exact results. For others, you will get approximate results. So now, enough about the theory. Now let's see what kind of results can you expect in practice. So let's have a look at molecule-in-molecule embedding. And here, basically, I have calculated the molecular binding energies. And please note that we are still doing DFT in DFT embedding. So you are not going to get anything better than DFT, but it just serves as a benchmark about the quality of the results that you can expect. So if we look at the weakly interacting systems, that is H2O dimer or HF dimer, then you see that method 1 gives reasonable accuracy if you compare to the green column of the reference DFT binding energies. And then if you also employ freeze and thaw and maybe a supermolecular basis, then you reduce the error, but still not exactly. However, then if you consider the strongly interacting system like the ethane molecule, where I have partitioned it at the carbon-carbon covalent bond, then you see tremendous errors with method 1 with or without freeze and thaw anyway. And then with method 3, after employing the freeze and thaw, because to get the self-consistent subsystem densities and also supermolecular bases, as I said, it is necessary for method 3, you pretty much get exact results whether the system is weakly interacting or strongly interacting. Then I have also implemented periodic in periodic embedding using this method 3 via the projection operator. And again, we see that if you consider the errors of the DFET total energies compared to the regular DFT energies, then you get micro Hartree accuracy. So something like 2 × 10⁻⁻⁶, 1.2 × 10⁻⁻⁶. And basically, how the system was defined was that, for example, if you consider the polyethylene 1D periodic chain, then the labeled or the transparent atoms were considered as one subsystem, while the remaining atoms were considered as the other subsystem. And then you perform embedding iteratively using freeze and thaw. And yeah, so, and also this supports multiple K points. So it's not just gamma point, you can do it for multiple K points, multiple periodicities. Yeah. However, till now, I have only talked about DFT and DFT embedding, so you don't see any improvement. And so what's the point? So now let me come to the molecule in periodic DFET. And this time we'll be using method 2. Earlier, I have already shown you what you can expect with method 1 and 3, but now with method 2. And this time we will be seeing an improvement because now we will be coupling the DFET with a wave function theory method like CCSDT. So to present the problem, so if you consider the absorption energy of the hydrogen molecule on the H10-1D periodic chain at various separation distances, then you see that DFT, the LDA DFT in orange, basically overbinds the molecule and predicts slightly shorter equilibrium distance compared to CCSDT. And this CCSDT is a periodic CCSDT calculation done using PySCF. So here you don't have any issues about the periodicity. Now, if I consider the purple atoms that I have marked as the cluster or the active subsystem of my entire system and perform DFET using method 2 for the embedding potential, then if you look at the green curve, then it is much closer to CCSDT results. So this gives a very nice benchmark or like demonstration of the importance of this molecule in periodic embedding. Next, I also consider this case of CO molecule on MgO001 surface. So this I have been doing recently. So here, the LDA-DFT predicts a binding energy of around 33 kilojoules per mole, while the experiment gives minus 13.5 kilojoule per mole. And we want to see how can DFET come into the picture to improve it. And I'm still working on it, so the results are not final, but basically I have till now tried 2 cluster sizes, that is 2 sizes for the active subsystem, the region of interest. So let's say COMG909 and then COMG707. And these are the results that I get for both of them using the method 2 for the embedding potential. So we still are quite a bit far away from the experimental binding energy, but this time actually we can again improve the result by considering the basis set superposition error, which I'm yet to calculate, and that will probably make it even better. Earlier in the previous result, I had actually just compared with CCSDT, so but here we are comparing with experiments, so we should also take care of the basis set superposition error here. So we'll see how this goes. And then we can also perform excited state calculations using DFET by coupling it with some wave function theory methods. For example, the second order approximate coupled cluster singles doubles, that is CC2. So here I consider 3 solvated molecules that are acetone, acrolein, and methylene cyclopropene. And I will consider the first excited state energy, or sorry, the excitation energy of these molecules calculated using the regular CC2 supermolecular calculation in the green column. And then I have the errors associated with different embedding methods, different methods for the embedding potential. And we see that the method 1 without the freeze and thaw, so FNT basically stands for freeze and thaw, by the way. So method 1 without the freeze and thaw gives just a maximum error of, let's say, 0.03 electron volt, which is quite good. However, when you employ freeze and thaw, then you get slightly larger errors. So that basically shows that we have some cancellation of errors happening where due to the kinetic energy density function, the error on one side due to KDF, and then the error on the other side due to not using the freeze and thaw. So that is why the result without the freeze and thaw somehow got better. And then method 2 is quite worse than method 1 with or without freeze and thaw. And this is because the environment density, as I mentioned before, is calculated using a very simplistic model. Then if we consider the adenine thymine base pair, and we calculate the first 6 excitation, 6 or maybe or 6, yeah, 6 excitation energies. Then in the green, we have the supermolecular CC2 calculations, and then we have the error associated with different embedding methods. And we see that again, method 1 gives just a maximum error of 0.053 electron volts, while with freeze and thaw, the errors for each of the excitations are slightly larger, but still the maximum errors are just like 0.042 electron volt. The method 2, similar to before, is actually the worst out of all these. And also, one very interesting thing that this embedding is able to do is, in the supermolecular calculation, actually, the second and third excitations corresponding to adenine pi to pi star and adenine n to pi star are, the DFT is able to predict the order of the excitations correctly, same as the supramolecular calculations. However, if you look at the isolated excitation energies, then you notice that the adenine pi to pi star excitation is actually higher than adenine n to pi star compared to the supramolecular calculation, but this is not the case with DFT. So again, this is quite useful. And we see tremendous computational improvements for both of these calculations, because if you consider, let's say, acetone in water, then you have somewhere around, let's say, 500 basis functions for the entire system. And then using just the basis functions of the acetone or the cluster that you define, let's say it's of about 20% of the total basis functions. So you see a huge improvement in the computational speed to get this approximately the same results, not exactly, but yeah. And then I have also coupled the DFT implementation with rt-tddft, where now I will show you the performance of the various embedding potentials and also the effect of the supermolecular or monomolecular bases. So here we consider the case of H negative and or rather just the LiH molecule with the two subsystems H negative and Li plus. And here I would also like to mention that in rt-tddft coupled with DFT, what we do is we keep the environment density frozen. That is, we evaluate the environment density, the ground state of the environment density, and then we just plug that into the embedding potential. And then the cluster density is actually evolved in time, but the environment density is kept frozen. And then there is also an option where both the cluster and environment density in the formula of the embedding potential will be kept frozen, while the cluster density in the remaining portions of the Hamiltonian will be evolved in time. But yeah, there's no option to evolve the environment density, because then you have to employ an iterative procedure. That is, you evolve the environment density for some time step, then the cluster, and then we don't really see any computational advantage. And also, since my ultimate goal is to study molecule in periodic, and we anyway cannot do any periodic rt-tddft, so that is not really beneficial for my ultimate goal. So yeah, so here I'm calling this LiH excitations as uncoupled, because as you can see here that the isolated H negative excitations are somewhere till 30 electron volt, while after 40 or 50 electron volts, you see the Li positive excitations. And if you look at the complete absorption spectrum of this LiH molecule, then you see that it is quite different to the isolated spectrums. So, it's not like even the isolated is able to predict these. So what you can do is, here are the results with method 1 of the DFT, and I employed 5 freeze and thaw cycles to get a self-consistent ground state and subsystem densities, and also a monomolecular basis. And here we see that it works in some areas. Some peaks are being reasonably described. However, some absorption peaks are still being missed by the method 1 in the monomolecular basis. And then we have the method 2. And although earlier I showed that the method 2 gives larger errors compared to method 1 usually, but here again we see while the errors of the peaks, peak positions might be larger, but the qualitative description is basically the same as method 1. So method 2 is not so bad. If you still get a qualitatively good description if you compare with method 1, not with the regular rt-tddft spectrum. Then I have the method 1 with the supermolecular basis, and now you see much better than before description. but still some peaks are being missed. Some excitation energies are under or overestimated, but still it is much better than before. And then I have with method 3, the projection operator embedding. And here we see with monomolecular bases, as I said, it should not work and you get just not even a good qualitative description. But with the supermolecular bases, as expected, we get 100% exact match. And the reason is that the excitations were uncoupled. So we were keeping the environment density frozen in time to the ground state, but it didn't really matter because the excitations in the cluster didn't really influence any of the excitations in the environment. And by the way, I forgot to mention, so these spectrums are calculated by considering Li positive as cluster and H negative as the environment, and calculating that spectrum, and then doing the reverse, that is considering the H negative as the cluster, Li positive as the environment, and then calculating the embedded spectrum and then superimposing those two spectrums. And yeah, so for uncoupled systems, as I said, method 3 can give you an exact match. However, now if you consider a system of interacting chromophores like benzene fulvene dimer at a separation of 4 angstroms, it's still not extremely interacting, but still there are a lot more interactions because the isolated absorption spectrums of benzene and fulvene overlap quite a lot. And now if you see that with method 1, in the supermolecular bases, we get somewhat reasonable description, but still the excitation energy, the amplitudes are, the intensities are actually overestimated, but the qualitative description is still okay, reasonable. And with method 3, it is now not exact as before because the excitations in the cluster will influence the environment, and we are not considering that, but still it gives a much better qualitative description as well as a quantitative description of the rt-tddft spectrum. Now, again, here we are using a supermolecular basis, so essentially we don't have any computational savings, but rather we have increased the computational requirements. But actually the next step would be to then consider a molecule in periodic system. So since we anyway cannot do anything about the periodic system using rt-tddft, so even this would be a good idea to, even if we have to employ supermolecular basis, at least we can study molecule in periodic systems in this manner. And then I have also extended the existing rt-tddft code with to perform high harmonic generation simulations. So basically, in high harmonic generations spectrums, to calculate them, you take the time-dependent induced dipole moment, and if you are doing the calculations in length gauge, then you can just take the Fourier transform of that. Or for example, here I am taking the second derivative, that means I'm in the acceleration gauge, and then you calculate the spectrum and plot it as the log of this P of omega on the y-axis and the frequencies on the x-axis, and you get somewhat this figure as shown in the upper right corner. So the first few peaks, the first few harmonics are called to be in the perturbative regime. And then you have the plateau region, and then you have the cutoff region where the harmonics start to die out. So essentially I use this kind of a laser pulse. So it's a sinusoidal pulse with a cos squared envelope function. And here is a test calculation on the benzene molecule. So a very simple calculation with just the SVP basis set, PBE, XC functional. And we already see that it gives a quite a good agreement with what you should expect from theory and intuition. So since so the electric field was applied along the y-axis, and since there is an inversion symmetry along the y-axis, we should only expect odd harmonics because you have a destructive interference of the even harmonics. And we see that we do only get the odd harmonics and quite a reasonable spectrum. However, there is one caveat that since we are working with turbomole and Gaussian basis functions, so you have this problem of not being able to describe the continuum states. So therefore, this method is only suitable as long as you are in the first few harmonics range, not going beyond the ionization energies, because then you will, one thing you can do is you can employ a ghost atoms around the main molecule. That will work, but then you also need to apply some kind of an absorbing potential around the some boundary. And I have been also testing it out, but I haven't been able to work it out successfully yet. But then also I did a test with circular electric field. And here again, as expected from theory, we get the harmonics that are multiples of 6 plus minus 1. So like 1, 5, 7, then 11, 13, and so on. And then we, instead of working with a test system, we collaborated with project in, so basically my PhD is within the NOA project, where we also have some experimental projects, and we collaborated with one of those, and they performed some ZN-TPP and TPP high harmonics generation experiments. And also we collaborated with another theoretical group that basically worked with octopus. And so here is the spectrum that we obtained, high harmonic generation spectrum that we obtained from TURBOMOLE above and octopus below. And in the orange, we have ZN-TPP. In green, we have the tetraphenyl porphyry. And we see that both give qualitatively a reasonable agreement with each other. So for example, the first 4 harmonics are reasonably well defined in both the codes. And then for the 9th harmonic, we see that in both the codes, the ZN, I mean, maybe I'm drawing too much into it, but basically, we don't really see any big difference between the two spectrums, and we observe odd harmonics as expected due to the inversion symmetry, same as in experiments. And we also observe this 8th harmonic for the TPP, same as in octopus, that there is a small 8th harmonic due to maybe the molecules not being completely aligned. So you will still have some small contribution from the even harmonics. And then also this is the comparison with experiments. So here they in their experiments, they cannot really go beyond the 9th harmonic, because then they damage the sample, because that is more than the ionization energy. And that is very good for us, because our code, since it uses Gaussian basis functions, also cannot really handle the cases beyond the ionization. So this code is perfectly suitable to model or maybe add support to such experiments where they are also staying inside the energies that are less than the ionization energies. So yeah, so that, and also, yeah, so this, so again, in experiments, they observe, as expected from theory as well, that as you go to the circular polarized light, the intensity of the harmonics will reduce, because then the chances of the recombination of the electron when it comes back to hit the towards the atom will be less due to the circular polarization. So basically, the highest intensity you get from linear polarization and lowest from the circular. And that is also something we were able to reproduce for both. I actually forgot to add the labels. So the graph above is for TPP, while the graph below is for ZN-TPP. Actually, I forgot to add the labels. That's my mistake. But yeah, so we observe the same behavior as in experiments, that as you go towards the circular harmonics, and the intensities get lower. And one interesting thing that you can also do with the code is you can observe the electron density in real time. So I will actually have to stop the screen sharing right now and switch to my desktop screen to be able to play the video. So just bear with me for a moment. And here it is. So you can also, if you want to have a more closer look about the excitations in the, or like how the electron density behaves under the influence of the electric field, you can perform such simulations and get these kind of animations. So, And from these animations already, you can see that both ZN-TPP and TPP act so similarly under the electric field that we hardly see any difference in their harmonic spectrums, and similar is the case here. So yeah, and yeah, so in conclusion, the FET using Gaussian basis functions is actually quite a useful tool to study hybrid systems. And I have implemented molecule in molecule, periodic in periodic, and molecule in periodic DFAD using efficient techniques already existing within the RIPPER module. And coupling it with wave function theory methods also offers an improved description of both the ground and excited state properties. And coupling it with the rt-tddft also offers a very reasonably accurate absorption spectra. Then in future, or what I'm doing right now is working on to implement molecule in periodic DFAD using projection operator that will require the supermolecular basis, but it will still be really essential or really useful to perform this molecule in periodic embedding exactly, at least somewhat exactly, if they are too much interacting. And then also I would like to couple the FET with high harmonic generation simulations, and because that is related to the aim of my PhD project, and benchmark and improve the efficiency of this code, because right now it's in a very like beta version state, and explore some ways to circumvent the use of supermolecular bases, because there have been studies about using the truncated basis sets, because as I said, so FDE already existed before, and even the projection operator I forgot to mention has already existed for like 10 years or 8 years now. And so it would be interesting to take some use cases about or some studies about the truncation of basis sets, and then also implement some code to calculate the polarizabilities, hyperpolarizabilities, and so on. And I would like to acknowledge my professor, Marek Sierka, for his guidance and support always, and NOA project for the funding, and TurboMOLE for the development support. And thank you for your attention. I'll be happy to answer any questions now.
Thank you very much for your interesting talk.